Welcome to this video about feature selection. Feature selection is the process in which we're going to try to automatically discard some of the features of the original dataset because we believe they do not provide relevant information for the problem, or that the information they are providing is already contained in some other features. The less features we have, the more efficient from a computational point of view the analysis of the data will be. And furthermore, what is more important, the less dimensions our feature space will have, and the more simple, the easier will be for the different algorithms that we're going to apply over the data to learn regularities in that space, and that those regularities are not due to an artifact of the sampling, are not due to irregularities found because of the curse of the multidimensionality, but they are true regularities in the data. We're going to start by dragging the iris dataset, as many other times in these videos. We're going to connect the output of the iris to the output of the process, and among the operators I'm going to look for feature weights. These are 17 different criteria to judge how each individual feature how good is in each individual feature. The fact that we have so many criteria is already a good clue that no one of these criteria should never be taken as a universal truth. They are more like rules of thumb that can be helpful, but we do not have to follow them blindly. Weight by information gain is going to use the criteria the same criteria that is used to build in decision trees. It will try to use every feature as the root of a decision tree and compute the gain in entropy when making a decision based on that feature. It's going to be following the same calculations that we saw to build a decision tree in the notes of the course. If that attribute is providing a lot of order, when choosing that attribute, the different branches of the tree present a lot of order, the different leaves have most of the instances belonging to the same class, the score will be higher because the gain in entropy will be higher. Gain ratio is a similar measure as information gain, but which penalizes features which produces a lot of branches in the decision tree. If we had a unique identifier in our dataset, by using that unique identifier as the root of the decision tree, we will get perfectly pure leaves, where each instance is in a leaf by itself. Of course, we know that unique identifiers are useless from the analytical point of view, and that makes no sense. Gain ratio uses the same entropy-based metrics as information gain, but it corrects that measurement by how many branches do I have to use, and the more branches I have, the worse that attribute it is. And in the case of a unique ID, I have a branch per instance is my worst case scenario. Let's look for some other technique based in a complete different approach. Relief, it uses random sampling of the data. It randomly chooses one sample, and then it searches for the closest point, the closest sample in the feature space to that other sample. If the closest point in the feature space to the one I have chosen randomly belongs to the same class as the initial point, that means that points which are together in the feature space then tend to belong to the same class according to that feature, and that add a +1 to the score of relief. If they belong to different class, that means that points closer in the feature space, according to that feature, they belong to different classes, and therefore that feature is not really good to separate those classes. And for example, we may use also weight by correlation. Weight by correlation computes the correlation among an attribute and all the other attributes, and the higher that correlation it is, the worse that attribute is considered to be, because its information is already present in some other attribute. You can see that I'm using 4 different techniques to measure the relevance of the different features of the iris set. I'm using 4 because, again, all of them, they are more like rules of thumb. And if I'm really going to trust the results, I would like to be more or less consistent criteria regarding the usefulness of a feature for all the different techniques. If I run this process, I'm going to get 4 different scores where, for example, according to correlation, the ones who get better score are A3 and A4. According to correlation, actually the one who is supposed to be the best is the one which is the lowest correlation, so A2 will be the best feature. The others, they do acting in such a way that the highest is better. And here, for example, A3 and A4 are supposed to be the best features. The same happens for gain ratio, and the same happens for information gain. There is some disagreement regarding features A1 and A2. Some of the techniques believe that A1 is the worst one, others believe that A2 is the worst one, but there is quite consistent agreement among the different techniques that the best features are A3 and A4. If we remember the behavior of the features of this dataset, I'm going to plot histograms for each of the features, and I'm going to show the different classes in color better. Let's go for histogram color so we can see where the classes lie. If we plot the histogram of feature A1, we see a lot of overlap between the 3 different types of iris flower. The same is true for feature A2, a lot of overlap. For feature A3, however, all the iris setosa is to the left and the iris virginia and vesicolor are to the right. There is a little bit of overlap among them, but much less than in the previous cases. And for feature A4, more or less, I get the same scenario for feature than for feature A3. That's why all these scores I have got, they seems to be reflecting true structure in the iris dataset. And after having plotted those individual features, and after checking that the different techniques seems to agree that A3 and A4 are the best features, I will be willing, if I had too many dimensions, it is not the case, but I will be willing to consider discarding A1 and A2, for example, because they seem to provide less information. However, if we go back to the data and we plot a scatter plot and we plot A3 versus A4, we're going to see that both these features has a really high correlation. They are both of them providing more or less the same information. While these two may be the best features, taking an isolation to try to classify the iris flowers, maybe after I already have taken into account one of these two features, A3 or A4, whatever of them, maybe the other feature I should take into account should not be the one remaining from the pair, but A1 or A2, because there is less correlation between these features and A2 and A1, and less correlations means they are providing different type of information. So maybe after considering the information present in A3, considering A4 will provide much less information than considering A1 and A2. When I'm using this type of feature weight approach, I'm evaluating each feature in isolation, and therefore I'm not evaluating sets of features. If I want to evaluate a set of features, I should use model-based techniques. In these model-based techniques, these feature selections are the ones which are model-based. Let's, for example, use the brute force approach over the data. In these feature selections, these operators are nested operators that you can see that they have a different look than the other operators we have used so far. If we double-click inside the operator, we can build inside the operator a predictive model, which is going to try to predict what is the right type of flower for the different instances, and it's going to count how many times the predictor gets it right, and it's going to do that for different sets of features. Concretely, the one we have used is brute force, and it's going to try every single combination of features. It's going to try each of the 4 features by themselves, each possible pair of 2 features from the iris datasets, each possible set of 3 features and the 4 features together. And it's going to train the model, whatever model we want to use here, with all those different sets of features. It's going to compute some performance metrics and choose which one is the best one. In the case of brute force, this approach of trying everything typically is not feasible for real-world datasets, because after we have more than 15-20 features, trying everything is not feasible. And we may have to use other techniques, such as, for example, forward selection, in which we start with a single feature and then we run the model, compute a performance metrics, and then we add a second feature, we rerun the model, and we see the performance decreasing significantly or not. If there is not a significant increase in performance, we discard the feature, and we keep proceeding that way, trying all the features. We keep adding features. If the performance goes up, we keep the feature. If not, we discard it. Backwards elimination, it will start with every single feature, compute the performance of the model, discard one feature, compute the performance again, and if the performance does not decrease significantly, it will discard that feature permanently. If the performance has decreased significantly, it will put back that feature and try to eliminate another one. And the evolutionary selection is based on genetic algorithms in order to decide which are the best combinations of features. It will use genetic algorithms to come out with different combinations of features. So we're going to use the brute force selection, given that that's feasible. We're going to split our data. In order to have a set of data to train the model, we're going to use the split is going to be 70% for the training and 30% for testing the accuracy of the model we have learned. We may use, for example, naive Bayes is one of the models we'll be covering in the course. 70% of the data is going to go to naive Bayes, and after that we're going to check how good is the model we have trained. This is the model we have trained. I'm connecting it to the apply model operator, and we're going to apply it over the 30% of the data that was not seen by the model. And we're going to count how many times the predictions were right by using the classification performance, which is really computing accuracy. It's counting how many times we are getting it right, and the higher the better. So within the brute force operator, that's what we're going to do. Split all the iris dataset, 70% for training the model naive Bayes, and 30% for applying the model we have learned from the other 70% of the data over the 30% remaining of the data, and then compute how many times did we get it right. And if we connect the weight output to the output of the process, in this case, I have just 0 and 1 weights, and that means whether we choose whether we keep the feature or not. And this technique is telling me to keep just the 4 feature, because despite the third feature, according all the other techniques which evaluate a single feature at a time, the third feature, A3, was pretty much as good or better than A4. Was equivalent to A4. However, both of them are highly correlated. They are providing the same information, and by using a wrapper-based technique, we have realized that indeed they are providing the same information, and once we have considered one of the features, the other is providing very little additional information. We want to apply the same analysis to a different dataset. It's going to be the Titanic dataset. I'm going to connect the output to the Titanic to output of my process, and now if I try to run the process, I will get an error which is telling me that there is no label in the Titanic. All these techniques that we are covering, they can only be covered for label data. I need to have a subset, at least, of my data for which I know the tooth crash to which the instances belong to, and those are going to be used for selecting which are the best features. But if I have all my data unlabeled, I cannot apply this type of technique. Let's suppose that my goal with the Titanic data is try to be able to predict who is going to survive and who is not going to survive by taking into account all the information I have, such as, for example, the gender, the age, or whether they were traveling in first, third class, and so on. So let's suppose that was my predictive goal. I'm going to use the set role operator to change the attribute survive, which initially for the Titanic data is just a standard attribute. I'm going to change the attribute survive into a attribute type label. That's what I would like to predict. And I think I'm also going to change the brute force selection, because I don't honestly think it's going to be able to run all the different tests for the Titanic dataset, because it's going to be just too many trials. So I'm going to cut what I have inside the brute force operator. I'm going to go for the evolutionary one. I'm going to use exactly the same setup as before. Here in the evolutionary operator, I can change parameters such as, for example, how many populations. Let's go for 15 populations instead, just 5 populations, the size of the population, the mutation rate, and some other parameters may be configured in this operator. Let's run this process now. And for example, let's start analyzing or checking the result of the techniques which take into account a single feature at a time. If we go, for example, for gain ratio, it's telling me that sex is the most useful feature, followed by age. If we go for example, relief, in this case all the features have quite low scores, because most of the times the closest passenger to this passenger belong to a different class. Say age and sex are more or less in the middle of the table. Negative is bad score. I would like the score to be as positive as possible. And it's telling me in this case that passenger, class, and fare are the most useful attributes. If I check weight by information gain, it's going to be telling me quite clearly wrong results. It's telling me that the name of the passenger, the ticket number of the passenger, and the cabin number are the best attributes. This is a good example of the difference between information gain and gain ratio. For information gain, using the name of the passenger as the root of the tree is an optimal solution, because it will yield perfectly pure leaves, because by using the name I'm branching as many times as instances, and each leaf I have a single passenger, which of course either survived or lived. And that's a useless piece of information. I could have discarded this without really applying feature selection techniques. I don't really know it to go that far. However, in information gain, this is not taken into account. The same happens for ticket number, which is also almost unique identifier, and cabin. There are several passengers which may travel in the same cabin, but most of the passengers are traveling in different cabins. In the case of gain ratio, these attributes are not the best ones, because they have been penalized for having such a high branching factors, and age and sex are preferred. If we, for example, check the correlation, also sex has a very high score over here, and if we go to the evolutionary algorithm, in this case sex was not chosen, which is a little bit surprising. It's choosing name, and it's choosing the lifeboat of where the passenger is. So these results are not really good either, because we shouldn't really be choosing if the passenger is in a lifeboat, very likely survive, because if it made it to the lifeboat, it did survive, and if not, it died. In this case, if we refine a little bit the analysis and we have removed a few features from the analysis, for example, if we just select attribute, and in the select attributes I'm going to use a subset, and I'm going to tell it to remove the ticket number. I'm going to tell it to remove the name, the cabin, and also live vote, because it's like cheating. You know, if we know that they made it to the live vote, almost all of them, when they made it to the live vote, they survive. By default, the select attribute, it only lets through the attributes that we have selected here. Actually, I have selected the attributes I would like to remove. So we're going to invert the selection, and let's rerun the process after having applied just some common sense. And now, for example, it is selecting sex and age as attributes, useful the model wrapper technique. And gain ratio is telling me that sex and age are the best attributes, and information gain is also telling me that sex is a rather good attribute. If we plot all the Titanic data, we'll be able to realize quite soon that indeed at least the gender of the patient, the gender of the passengers, is quite clearly an usable attribute. Let's plot here survive, and let's plot here the sex attribute. Let's add some jitter in order to interpret the data. And we see how this is male, this is survive, this is died. Many more dots here, many more men died than survive. This is female, this is survive, this is died. Less woman died than survive. So if you were a female, you were more likely to survive. If you were a male, you were more likely to die. Therefore, the gender of the passenger is useful for predicting whether the passenger is going to survive or not. And therefore, the different techniques that we have been using are right to tell us that the sex is probably the most useful attribute. Again, when applying feature selection techniques, we should first use common sense, remove identifiers, and if we have some piece of data where we have a lot of missing data, we may also remove that. Besides that, we should also consider these techniques and see if there is something quite clear that all of them are pointing. If there is something clear, if most of the techniques seem to agree that a given attribute is not providing value, then okay, go ahead and remove it. But if most of the techniques are not giving you that type of information, then you should be a little bit more wary, because after all, they are just rule of thumbs, and especially if you don't have too many features for the amount of data you have, you should move forward with all of them. Furthermore, some of the techniques that we see to analyze the data, they also have implicit within the technique some feature selection stage. Not all of them, but some of them they do. RapidMiner has a feature called Auto Model. I think we can just, or excuse me, Turbo Prepped. In Turbo Prepped, let's load the Titanic data. Turbo Prep is trying to tell us which features seems better quality or less quality by scoring them according to 4 different quality criteria. In these quality criteria, green means good and red means bad. So it's trying to tell us that, for example, live vote and cabin do not seem to be very good features, because in this case they seem to behave like IDs, and they seem to be unique identifiers. And that age, the reason why it's red here is because it has a lot of missing attributes. So the meaning of the 4 bars on top are The first one is how many attributes I have missing. If I have a lot of attributes missing, that's a bad sign. If most of my instances have that attribute missing, it's going to be useless. The next one is, does it look like a unique ID? For example, for the ticket number, that attribute should be much higher. Okay, now it doesn't want to show me the... Okay, it appeared. Here is telling me that this looks like a unique ID, and that's the largest issue that it has with the data attribute. And for the case of cabin, again, the problem in this case is that for most patients, passengers, we don't know to which cabin they belong to. In the case of lifeboat, the problem is that for most of the passengers is missing. So it's trying to give us a clue automatically of which features seems to be better and worse features. This is a pretty new functionality within RapidMiner. It is fine. It's trying to have 4 different scores. For example, in this case, it's pretty sure that this is a unique ID because 99.85% seem to have the same value. And that's telling us that it's a bad feature because it looks like an ID. The stability, for example, is a measure which is checking how many instances have the same value for that parameter. In the same way, we don't like attributes which are different for everybody because it's a unique ID and is useless for analyzing the data. We don't like attributes which have the same value for everybody, such as, for example, if we were analyzing patients from a hospital and we have selected only patients which had breast cancer, then the gender of all those patients will be female, and the attribute female, therefore, it will be useless for diagnosing breast cancer. So that's what the stability measure is using. This is a nice attempt from the part of RapidMiner people to try to have concrete criteria regarding the quality of each of the features. It's a quite recent feature within RapidMiner, feature in the sense of functionality of the tool. And they'll probably be evolving it in the next versions, because when I'm doing this video, this functionality has been here for literally just a few months. But it can be helpful to check if we have too much red, which is showing us that it's bad, or too much blue, which is showing that this looks like an ID. Over here, in case you are curious, is showing me the histogram of the different attributes. So these are a representation of the histograms. Well, that's everything for this video. I'll see you in the next video, where we're going to start already training different models.